Okay, this is good. Uh, quit moving the mouse around. My name is Eric McRae. You heard that much. I'm a principal electrical engineer, and that's sort of title only, having to do with working for the University of Washington in the state. You have to have sort of title grades at the applied physics lab. There are a number of principal electrical engineers, so I'm just one of many. And so the title doesn't mean much, because I do a lot more than electrical engineering. My background, I started out in computers. Whoops, let me keep this off to the side. I started out in computers 1976, and worked for Burroughs Corporation, if anybody out there remembers, an old business computer company, and moved on to work for an avionics company, Sunstrand Data Control, and then eventually to a little company that I doubt anybody knows. It was a classic electronics startup called Applied Microsystems, real generic name. And I joined, I was the 5th employee, and I left it about 11 years later, and there were 380 employees. So it was quite a ride. It gave me the confidence to go into business for myself as a consultant in control systems. And so since 1992, I've been, well, starting in 1992, I had this business, and I ended up having some pretty wonderful clients. Ford Motor Company was one of the biggest. If you have a Ford vehicle that was manufactured anytime between 2002 and about 2013, my software runs the engines in those vehicles. I've worked for McRae Computer, did the control and cooling system for one of their supercomputers. Like I mentioned, I've done some aircraft computers, and even worked on pacemaker defibrillators. So I'm real into control systems, kind of no matter where they lie. And of course, I got very intrigued, along with lots of other people, about robotics, and have looked for ways that I could work in that domain. So I live in a small town on the northwest part of Washington State, and I live on saltwater. And when I moved here in '96, and fell immediately in love with the ocean and saltwater. And I've been a diver for quite some time, and just the combination was just so intriguing to me. There was so much to learn about, and so much to I eventually reached a point where I said, I want to contribute to that before I retire. So 2011, I took a job at the University of Washington Applied Physics Lab. The Applied Physics Lab is it's a pretty big facility. There's about 300 people that work there. It's not an academic part of the university. It's what's called a university, a UARC, a University Associated Research Center. And that's a Department of Defense designation that allows the lab to take on certain of the Department of Defense divisions, particularly the Navy, because we were the lab started in 1943 during World War II. They needed a way to both create targets that Navy submarines could attempt to shoot torpedoes at, and then they also, the biggest thing was they developed a torpedo exploder electronics in the torpedo that would sense when it was going past a ship and would explode. That's so that they could turn near misses into actual detonations against enemy ships. Well, okay, so that's how it started, and it's now way branched out. The military is not, it was 100%. I think it's down to 40% or something of the lab's funding, and we now are funded by the National Science Foundation, National Institute of Health, NASA, um, and several other organizations. And so the lab has branched out quite a bit, but has retained its most of its work is around the ocean. So pardon me if I keep turning my head that way. I have my notes over here, but I'm going to just talk about the groups in the lab for a second. We have a polar science group, an Arctic research group, which is every summer spends months up in the north, either on a ship or in ice camps on the ice, and they're studying what goes on top of the ice, studying the ice itself, and what goes on in the water below the ice. There's an ocean physics department which studies how the oceans move. And I've learned some amazing things in there. But I'll just toss out one little tidbit, that there are waves in the ocean that are under the surface. And these density waves are huge and significant to the function of the ocean, if you will, but something anybody that's just looking at the surface doesn't particularly see. There's an air-sea interaction group. So a group that looks at what goes on between the air and the water, how the energy from the waves affects the air, how the humidity, all sorts of things. And that group is, in order to do that, needs to, they're heavily involved in remote sensing. So they developed vehicles and tools that can be placed thousands of miles away from shore and still communicate with them clearly through satellites and so forth. There's an ocean acoustics group that studies how sound travels in the ocean in various forms, both for measurement, for knowing how the water is flowing. I can't even begin. It's a fascinating group. I could be in that group if it wasn't for the fact that I love the group that I'm in. There's a medical ultrasound group. They're heavily involved in, particularly into kidney stone manipulation. They've developed tools that can break up large kidney stones. We've known about that for some time, but then they have the ability to drive the kidney stones through the passages in the urinary system and out. And so it's pretty amazing group. There is an ocean engineering group, which is basically hired guns for anybody who wants to pay the bill to develop instruments or equipment that you can be pretty guaranteed are going to work well in the ocean. There's a group called Environmental and Information Systems. Okay, so it's kind of a catch-all, but one of the things they do, there's a small group within that group that studies the chatter on social networks and their goal is to identify terrorism, terrorist cells, using statistical analysis of chatter. And so that's a tiny part of that group. They also do all sorts of environmental studies like glacial degradation, and there's many other things. But and then finally, there's the electronics and photonics system, and I'm a member of that group. That group is where there's a portion of that group that is involved with most of our Navy contracts. which vary. We don't do weapons research, but we do data processing and acoustical research for the Navy. Anyway, so I'm in that group, but I'm in a special part of it. And what I like to do right now, this is I'm going to play a video that is, first I have to stop sharing. Oh, let's see, how do I do this? Here we go. Yeah, I can do it this way. This is, for those of you who out there might be approaching my age, which is kind of hard to imagine how old it is, but there's been a development in videos in the last 10 years of sort of 1-2 second clips and then switch the subject of the video. And I'd like to punch whoever came up with that idea in the nose. I just hate it. But this video is full of that, but it does try to cover a lot of what APL does. So this is just about 3 minutes long. So I'm just gonna let it go out.
There it is. Now we hear it.
Okay. So, excuse me. So if there's anything that that video would demonstrate, it's that there's an awful lot of things going on at the lab, and different groups. As an engineer, it is really a lot of fun to be able to pick people's brains. If I want to know about a certain kind of acoustics situation, there's someone at the lab who's a specialist in it, and there may even be groups of people that are specialists in it. And so I said we have about 300 people, probably 120, 130 are full-fledged scientists, many who are co-chaired within the University of Washington. There's about 35 engineers, and then quite a bit of support staff of varying kinds. Yeah, but anyway, within that group, and particularly in my group, I get to work with scientists from outside the lab and across the country and world even. And the reason for that is because I work in a very specific project. Let's see, I'm gonna see if I can pull up this slide here. Okay, I work on something called the Ocean Observatories Initiative. And that's a National Science Foundation funded research project to put observatories in the ocean. And the University of Washington has probably the largest part of that project, in that we have a cabled undersea observatory. Well, what's that? That's basically what you can kind of think of it as putting a little power strip down for science instruments that allows them to be powered and also allows them to send data, communicate with shore constantly. So this picture, and it seems like every picture I find breaks all the rules about clutter on displays, but Seattle is up here, and there's a little tiny town, population 1,200, called Pacific City. And from Pacific City, 2 cables go out into the ocean. One goes about 320 miles out to the edge of the Wanda Fuca Plate. Now, I don't know how much press this gets down in the Colorado area, but this plate someday in the past has been, and someday in the future will be responsible for some extremely large earthquakes up here, because this is where the plate is growing from, its spreading center, and it's growing towards shore. You can see these arrows all along here, and the plate dives under the continental crust right there. So we have future research planned for this area, but right now we have a great number of instruments out here at Axial Seamount, which is a subsea volcano that is about 1 mile tall, and its summit is about 1 mile below the surface. We also have another cable which comes out, sits right on what's called slope, the base of the continental slope, and then that cable extends almost all the way to shore up to a depth of 80 meters. And all along that cable, and in several locations on the north cable, are these primary nodes. You see PN5A and PN3A. Those are engineering designations, but basically those are like branch points in this network tree. So scattered around on this subsea network, I'll give you some examples. So shore is, the depth is 0. As you get out to southern Hydrate Ridge here, the depth is 600 meters. but then it falls off. Slope base is our deepest site. It's 2,900 meters deep there. That's a long way down. And in fact, axial base, where this little circle is out here at PN3A, is a little bit shallower. It's 2,700 meters. And the reason it's shallower is because that's where the plate is growing. All along this plate are thermal vents scattered here and there. And of course, axial seamount, being a volcano, is a large source of thermal activity. In fact, that since we've been doing research out there, that volcano has erupted 3 times. And the last time was in 2015. And we had, at that time, we had instruments. This network, this observatory was built starting in 2013 and was fully commissioned by 2015. So we had all sorts of instruments in that, on the side of and on in the caldera of that volcano when it erupted. We were fortunate that it did not damage any of our equipment, but which it easily could have. For some reason, it ruptured out the north side of the volcano and extruded about 14 cubic kilometers of lava into the cold water. Now, I'm going to jump around a little bit here, but I want to play for you. Let's see. I'm going to have to do this the hard way again. This is the sound recorded by one of the hydrophones. A hydrophone is an underwater microphone, basically, and we sample these things at 128,000 times a second. So they're broadband hydrophones, and so we get exquisite data. This particular hydrophone was about 14 kilometers away from where the eruption occurred. But I'm going to do my little trick here and play this for you. I'm going to skip ahead here. Let's see. So I don't know how well that came through, but it sounds like rumbling that you would hear down a long tube or something. But this sort of sound, the sound pressures from this eruption were from this hydrophone and from other hydrophones, they were able to zero in. We have such precise timing in this network where we could listen to different, the arrival time of the sound at different hydrophones would tell us, we could see where the sound was coming from. And then we could learn a lot about it by the impulse that you hear, followed by a kind of a bunch of rattling. Well, it turns out what's happening is when the lava will sort of break out of a fissure and then immediately cool, because the seawater is at that depth is just above freezing. And so this molten rock hits the freezing water. And of course you get, first of all, you get a huge steam bubble almost immediately. And that bubble starts to rise away from the rock, and the rock begins to be, the lava gets cooled almost instantly by seawater, and then the bubble collapses. Well, both the creation of the bubble and the collapse of the bubble make sounds. And you could actually hear, it's probably difficult, I'm sad to say, it's probably difficult with my little audio arrangement, but if you stick that sound in your own headphones and listen to it, you can almost imagine the creation of the large bubble, the collapse, which is a big shock, and then the sound of lots of little bubbles coming off the still hot lava. Anyway, that was pretty exciting. This is one of those inside stories that happened on a Friday, and all of the engineers that work on this network share a floor in an office building, a small portion of the floor. And I remember one of my colleagues yelling out the door, "Hey, the axial's really shaking." He was looking at seismometer data, and we turned on the hydrophones. We can listen to this stuff in real time, and so can you. Anyway, we got to listen to that eruption, and the interesting thing about it is, as big as it was, it did not reach the surface. The eruptions from these volcanoes will create a hydrothermal plume that will rise up maybe 1,000 meters, but they rarely get to the surface. So it's really, and I don't quite understand that. I'm not a volcanologist, and I don't understand why it doesn't go all the way to the surface, but it does not. And in fact, it creates a plume of minerals that attracts plankton, and they think now that whales actually feed off these plumes, which last for months and months. So that's just one of the little things that goes on in the ocean that you just don't always get to hear about. My part, let's see, I'm not sure I don't remember what my next slide was. Yeah, okay, I played this. My part in this system was well, hold on, I just want to cover one of the things we have out there. Are video cameras, and this object here is a hydrothermal vent. It's mostly sulfide minerals that come from the superheated water. Now the water comes out of these fissures. Here you can see a sort of a magnified image of what's in this little square over here. And it's distorted because of the thermal differences in the water. The water coming out of the fissures is often around 320 to 350 degrees C. You could start a fire with it on land if you could get to those temperatures. But that hot water hits the cold water all around and immediately precipitates out minerals. In the process, it creates these structures. Now there's a little one in front, this dark one, but behind is also an older, larger structure. And what happens is eventually the structures themselves sort of become an insulator between the superheated water and the cold water. And there's many forms of biolife that can live on these vents. So this is a zoomed in picture of that very same formation. And almost everything you see here, with the exception of these little dark areas, everything else is something alive. All this white stuff are different critters, if you will. You've probably seen, these are the tube worms. You've probably seen pictures of these. I don't have a video of this, but these things move around, they wave around, and sometimes they eat each other, and other things come in and eat each other, eat things. It's just stunning. And so we have high definition video, which you can see, you can watch from home. I'll give you some links for that in a bit. That's just sort of the one visible part of our network, but another part is this, I talked about the earthquake. We send our seismology data to the Northwest seismology network, and they do that. They look at that data along with lots of other inputs to identify and locate earthquakes. And this is sort of a funny thing. From the 20 to the 22nd of April 2015, the leader of our project held a workshop in Seattle on what we should do if there was an eruption at this volcano that we've instrumented, and to talk to scientists. So we had about 120 people on site these 3 days. And this is the number of sort of daily earthquakes at axial seamount. So here's the conference. 2 days later, the number of earthquakes went up. And this is when the eruption occurred. It was just, unbelievable number of earthquakes per hour, 600 per hour. And so everybody thought this guy was pretty smart to hold that workshop right then. We not only have instruments that feel the shaking or listen to the sounds, but we have these exquisitely sensitive depth sensors. So this blue trace is the reading from a depth sensor that was sitting in the caldera of the volcano. Now it's a caldera. It's not like the ones in Hawaii. It's largely cold, hard rock. But we have these scattered around. And then this red trace is a measure of the seawater. So you look over here, it's sitting around 2.9 degrees C. On this day was when the eruption occurred. So you can see that that sensor dropped from, its depth increased. So it went from 1509.75 approximately down to 1512.25, almost 3 meters or 12, not quite 12 feet, 10 feet. It dropped all of a sudden. It did that drop in about 2 hours. So that means that the caldera, this caldera, which is 3.5 kilometers wide and about 14 kilometers long, it sunk down that much, at least at that site. Meanwhile, the water temperature in the caldera went up quite a bit. Now that's only, it's not even a degree C, but it's a huge volume of water. So there was a tremendous amount of thermal energy just released, and this wasn't where the eruption was. So it's data like this that is produced by our network, and again, this is freely available. Any of you can get to this data if you happen to be interested or want to be. I can sort of get you started in that direction. But of course, there are a great number of scientists, established scientists, who are using this data. So the one thing about a cabled underwater observatory is that the data is continuous. Our slowest instruments are sampled once a second. And never before has anybody been able to get a reading once a second every day, 24/7 for a year, years and years at a time. We have this network is producing all sorts of data. And I haven't really told you the different instruments. There's instruments for geology, there's instruments for ocean physics, in other words, how the water is moving, the temperature of the water. There's ocean chemistry, salinity, pH, temperature, of course, ocean biolife, both in terms of super small stuff, just chlorophyll-based organisms, plankton, up to shrimp size. We have sensors that actually can detect large fish and count them. We have sensors that measure tilt. This one's depth. There's sensors that measure tilt. They're used in the caldera to detect the swelling of the dome. So there's a large number of sensors available on this network, and the whole purpose of, let's see, I'm going to shut this off for a second here. Okay, I think you're seeing me now, right? Yeah, good. The whole purpose of this was that, you know, in the past, to do ocean research, people would have to hire a boat. They'd have to create equipment that they could throw off the boat or deploy from the boat, or sometimes ships of convenience. But in any case, they would generally have to be battery powered. And if you're looking at something on the seafloor, you'd throw it over on the seafloor, and there it would stay for as long as you thought healthy, and then it would have to pop up, or you'd have to go try to find it and recover it. And ultimately, there were two things that suffered. One was that because it was battery powered, you couldn't read the sensors very often. So, you know, there just wasn't, it wasn't a good way to do things. Your data was spotty. A lot of times you go to find your piece of equipment, it was gone. So anyway, this cable allows scientists to put their own instruments on it. We have a set of ones that are there all the time. And the one thing I just sort of, I'm getting near the end of my time here, but I wanted to talk about is my part of it, which is, let's see, let me get out of here. My part is what's called the shallow profiler. There are 3 machines whose, let me see if I can find this. Sorry, I'm losing my, there we go. There are 3 machines that geez, my apologies. I've lost my pictures now. 3 machines that sit up in the water column at 200 meters, and they carry science instruments from a mooring at 200 meters up to the surface and back 9 times a day. And it's sort of a similar thing. All of those instruments are on all the time, and are streaming that data back basically onto the internet, so anybody can see it. The data is also recorded, and if you want to look at historic data, that too is also available. So let's see, where's I lost my pictures here. Science Sparks, there we go. Well, okay, I don't see it, and it isn't so important. I'm going to direct you to a couple websites. Let me go back to sharing my screen. Apologize to everybody for jumping around so much, but so these 2 websites, oceanobservatories.org and interactiveoceans.org. The top one is the National Science Foundation funded website, and the bottom one is produced by the University of Washington. And in it, it's difficult in this short period of time to describe everything, but it will talk, the larger one, the first one talks about all of the observatories, of which the regional cabled array, my part of it, is one piece. The bottom one has to do mostly with the regional cabled array. So, you know, I could show you a million pictures and tons of videos, but I think I don't know, Phaedra, how much time do I have?
We're closing in. We got a couple more minutes.
All right, let's see. I think what I'll do is, let me shut that down. And I'm going to play we'll play another video because it's kind of fun. Let's see if this comes through. Oops, wait a minute, we did that one already. All right, we're not going to do that. I think what I'll do is, I apologize. I, would love to show you a ton of pictures of the my part of it, because of course I love it. But what's I think more important to me to express is that we probably know more about Mars than we know about what's going on in the ocean. And so this kind of observatory is really sort of helping change that. And so my hope is that scientists will make use, and we're starting this. So 2014, what I realize is academia sometimes is it's difficult to get them to switch over to new things. But what has happened is we've had a lot of young researchers that start to look at this data, and they have to use different kinds of tools because the amount of data generated by this observatory is huge, and you can't, as a human, scan it. It's just, you might be lucky and find something, but it's just mostly you need to know software to be able to do anything helpful with the data. Not helpful, but to be able to explore it for certain things. So it takes a kind of a different mindset. And so one of the things that the larger group is doing is training. We hold lots of workshops to train scientists on how to approach this difficult thing. I'm going to show you, let's see, let's get back. I want to try one quick share again, share screen. Now we'll take this one, and I'm going to pull this paper in here, if it will show up. There we go. And so this is a paper that I wrote.
We're still looking at you, Eric, if you're trying to share your screen.
Oh, it didn't work. Okay, thanks, Phaedra.
Yeah.
Not only do you click it, but you have to say share. All right, so this was a paper I wrote for a conference last year, and I'm just going to scroll down because I want to show you a funny little chart. And so this would be impossible to see, but I'm going to zoom in here. Okay. So what we see here, the black line is depth. And this is the profiler I told you that goes up and down 9 times a day. And it's inverted. Wherever you see the straight line here, that's where it's parked. Down, it's this scale on this side, seawater pressure. It's down close to 200 meters. And then 9 times a day, it goes up to the surface and back down. And occasionally it'll step on the way back down. So this is where the little science pod with its instruments is closest to the surface. And this is where it's on the seafloor, or not on the seafloor, but down close to the mooring. This blue trace is dissolved oxygen. So dissolved oxygen usually is affected by critters that are turning sunlight into oxygen. So they're chlorophyll-based systems up near the surface. But what we see here, if you see this little bump, that's a bump in dissolved oxygen. Now, it could be that there's a current flowing through, but this depth is around between 160 and 180 meters down from the surface. So, that's 2 American football fields down. And if you look, so here's 7 p.m. or 7 a.m., I'm sorry. And then at 10 a.m., the situation is different. And then at 1 in the afternoon, it's different yet again. There's these peaks that show up. And so I just happened to look at this. This was, I can't remember the day. It was a day last year, but let me scroll down and look we just looked at one of those bumps. Let's see. I don't remember which one it was. Maybe it was this one. I scrolled to the left, and it turns out that not only were there perturbations in the dissolved oxygen, but there was a double layer that formed. And the difference in depth here is about 10 meters. As this sensor is going down, it's sampling once a second, and it only travels downward at 10 centimeters a second. So it's not moving very fast, but it's enough that it picked up these two layers. And part of the gist of this paper was, we don't know what happened. No one's ever seen stuff like this before, because no one's ever had data coming at that high speed, at that resolution through the water. So this was sort of a teaser that I wrote to present, to get scientists interested in this. So so that's it. I'm going to stop sharing, switch back to me, and I guess what I'd like to do now is throw it out to questions. I realize that it's difficult. This is such a huge and complicated system. It's a little difficult to do it in this period of time, but the gist of it is there's this large sensor network out there, and it's producing all sorts of data. And so, questions?
Yeah, thanks so much, Eric. Yeah, if anybody has any questions, unmute yourself, please.
Hey, Eric, give them a very quick explanation of that cable. I found was very interesting. It's not your everyday winch cable on a truck.
It's funny you should ask about that, because the cable that winches, so the science pod, what we call the science pod, the part that floats up with instruments, is 400 pounds buoyant, and it's about the size of a refrigerator. It's about 230 meters long, and normally on a normal day it travels about 190 meters. With the winch unrolls about 190 meters of cable. That cable has to carry power up to the science pod, and it also has two pairs of communication wires, two pair wires, four conductors total, two pairs of those, which are a primary and a backup communication channel. So those of you who know data rates, we have about 40 megabits a second data rate between the science pod and the winch platform where its home base is. That cable is also around those conductors is wound what's called Vectran, which is a little bit like Kevlar. Vectran strands. There's a winding sort of a web that goes one way around, and then outside of that is a web that goes the other way, because this cable alternates between being under tension, especially up near the surface. When there's waves, you can think of the waves lifting and dropping that science pod, so the cable will tension and untension fairly dramatically, and we didn't want it to spin. So that cable is what you call torque balanced. It's a 1/2 inch in diameter, and its breaking strength is about 6,000 pounds. So it manages to survive a year's worth of winding and unwinding under these varying loads, all the way. I mean, it's amazing to me that it survives. I mean, we even had to worry about things like shark bites on the cable. So to best of my knowledge, we've had a few nicks we couldn't explain, but we don't really know if we've gotten shark bites. But that cable is amazing. And there's one other thing I was going to say about it. The conductors. You think of the zip cord that you use to plug in a lamp or something in your house. There's conductors in there like that. There are multiple strands of very thin braided copper. But when you're working in the ocean environment, one of the bad things that can happen with cables is you can have a penetration in the jacket, which means that seawater can somehow actually reach the copper conductors. And so because of that, every grouping of stranded copper bundles is impregnated with this goo that is sort of like a gel, but it prevents water from traveling up and down the strands of copper with capillary action. So you could actually break this cable and expose it to seawater, and it wouldn't, if you don't do that, the extreme pressures will just push the seawater into those little air spaces and destroy your cable and your equipment pretty quick. So it's a pretty deluxe cable. I get to say hi to my brother and his wife out there. Yeah. Any other questions?
I got a quick question, if that's all right.
Yeah, Sam. Yeah.
Do you have any like special techniques on ways that you look for patterns in the data or anything, or does it depend on what you're looking for?
It's a great question, Sam. As an engineer, I look for things like variations outside of normal operation. And one of the things that I was just telling my brother about a couple of days ago is I have some code that monitors the tension in the winch drum, the winch motor drive, while it's pulling the science pod down. I can monitor the current that it takes it pulls it down at a constant speed. So any change in the current means that the load changed on the science pod or something else, if there's friction or something. Well, fairly early on when we were debugging, this winch has a level wind, kind of like a classic fishing reel that keep the line spooled very perfectly along the reel, the winch drum. And if the level wind gets out of sync, then the winding won't pile up right. And one of the things I discovered was that if the winding starts to pile incorrectly, often you'll get a snap where the cable jumps up on a cable next to it. So you got to think of this winch, the spool of thread. In this case, it's cable. And if the cable jumps up onto an adjacent winding and then snaps back down, that little snap is just a tiny little thing, because what happens is just briefly, as it drops back, the tension is released in the cable. And I could see that as a little tiny glitch in the current going to the winch drum. So I wrote some code specifically to look for any little sharp changes. Now that's my own engineering data, but that same approach can be applied to any of the data coming from these instruments. You could say, okay, this is a normal day. Normally things don't change real fast in the ocean. I want to look for sudden changes. And I mean, there's many ways. And one of the other things I want to say about this is because all of the data from the 150 different instruments is every data stream is time-stamped to within 10 millionths of a second. So if you get a timestamp, identical timestamps from two different machines, that that data was collected at exactly the same time. I didn't say that right, but you know what I mean, I think. So now oceanographers who don't normally cross from, say, ocean chemistry to biology can easily do that. They can correlate, because in the science pod, it's only a refrigerator sized thing. So what it's seeing on one sensor is highly correlated with, for example, a temperature sensor and a plankton sensor occur at the same time. So they can now scan through both of those chains of data and look for, indicators in one saying, gosh, every time the seawater gets warmer, we get more plankton or gets saltier or who knows what. So that's one of the things that's different in this observatory than what most oceanographers are used to. So we're having to train people and give them tools on how to do that kind of analysis.
And that pod, Eric, that's going up and down 9 times a day, how often does that need repairs?
Well, we go out every year. And in fact, as I speak, there's a ship offshore right now that 3 weeks ago replaced. I have 3 of those machines out there at 3 different locations. And every year we pull out the whole winch and science pod package. There's 2 reasons. One is there are science instruments that need to be refurbished. They have reagents that they run out of and so forth. So all the science instruments come off and get sent back to the vendors for recalibration and refurbishment. All of the wear parts in the winch system are replaced. And then we open up all the electronics housings and go through functional test, make sure that everything is still working the way it's supposed to, and then we put it all back together and test it in a saltwater tank and then take it out on the ship. One of the things I should say about working on a project like this, it's a little bit like a space shot in that once it goes off the ship, you're not going to see it again for a year, whether it works or not. And if it doesn't work, everybody knows whose project it was. So we do our darndest to make sure that everything functions when it goes over the side and keeps working for the entire year.
Hey, Eric. Are there other systems like this or other cables in different parts of the ocean, or is this the only one?
This is not the only one. It turns out that when the person who was trying to get this cable started back in like 2004, I think, approached the National Science Foundation, U.S. government, and they weren't interested. He had friends who were scientists in Canada, and they approached the Canadian government, and they were. So one of the first observatories is called Neptune Canada, or you can get to it called Ocean Networks Canada, and that was actually the first. And our lab contributed a fair amount of design to that system. It's not as big as ours. It still goes out to some very deep water. And, we sort of thank them because we learned from a lot of mistakes that occurred during that. But that network is still active and valuable, and we're on good terms with those people. At one point, so it extends out from Vancouver Island. It's a couple hundred miles north of ours, but we wanted to tie the 2 networks together, and that may still happen someday. Thank you all for your attention, and I've enjoyed this. I would love to have you for an afternoon up at the lab sometime. Maybe, Phaedra, we can do that. And,
yes, hopefully next year will be better.
It's pretty fun to see real things. Little tough to convey it from this little camera.
Thanks, Eric. It was very interesting.
Yeah, good. Glad you all liked it.